Lunch dessert is more math. So we just learned the LCT, the limit comparison test. We'll do things very quickly again. Intuition, and then the other way, the formal way. What does your intuition tell you here? Converge or diverge? It's an infinite series, okay? The terms go to 0, right? So the nth term test is inconclusive. But this does, if you simplify the leading terms, it would simplify to something that is similar to a 1 over n to the first, right? Because n to the fourth over n to the fifth is 1 over n. And of course, 1 over n does what? That's your divergent P series, known as the what? What's the special name? You see that? This is your harmonic series. So if you have like polynomial over polynomial, if you just simplify the powers, you can compare it to that. So this is the harmonic series which diverges. So guess what? This one also diverges, okay? Now to prove that, you would have to take the limit as n goes to infinity. And when you do the one that you're given, which is this long ugly thing, divided by the one you're comparing it to, notice when you do state change flip, dividing by 1 over n is the same as multiplying by n. All it's going to do is change the exponents in the numerator and make everything 1 degree larger. So it ends up being that. So if you could do that in your head, state change flip, and come up with that, that's fine. But when you compare it to the right thing, essentially you make the powers in the numerator and the denominator the same. You'll always have the same degree. And so the limit should always be what? Leading coefficient over leading coefficient, which is a fourth. And because 1/4 is greater than or equal to 0, I'll call that S at the top. S does what as well? Yeah, diverges. All right, this one I won't do, but what do you know about this one? Converges or diverges? Converges. You would compare it to a 1 over n cubed. Yeah, and the direct comparison doesn't work on this one, but the limit does. What about this one, intuition? Bless you. Diverges. You would compare it to 1 over n to the 1/2. Excellent. And when you do state change flip, this one is interesting. You'll end up with the square root of n over 3n minus 2. If you put them both under the square root, because you'll have the square root of n over the square root of 3n minus 2. If you put them both under the radical, then under the radical, the limit is 1/3. But then you take the square root of it. This is the square root of 1/3, which is still what? Greater than or equal to 0. So they're going to have the same behavior. So they both diverge. All right, alternating series. This one is pretty neat. And this one is usually pretty easy to spot. An alternating series is a series that alternates signs on consecutive terms, okay? You have some series that are plus, plus, minus, minus, plus, plus, minus, minus. Those are not called alternating series. It has to go plus, minus, minus, or minus, plus on consecutive terms. All right, and it's easy to spot in expanded form, right? You just notice that it's plus, minus, or vice versa. But in the rule of sequence form, there should be another plus there. There's usually the alternator jumps out at you, okay? Here is the alternator, -1 to the n plus 1. Because for consecutive positive integer values of n, that becomes -1 to the first, which is -1, -1 to the second, which is +1, -1 to the third, which is -1. So it doesn't contribute at all to the magnitude when it's being multiplied. It only contributes the sign. So here are some famous alternators. Famous alternators. Of course, you already met this guy, -1 to the n plus 1. It could also be -1 to the n minus 1. Okay, it kind of works the same way. And of course, it could be -1 to the n. Those two, the ones on the top and bottom, those are going to alternate terms interchangeably. The first one, if you start with n equals 1, is going to start with an even term. The bottom one, if you start with n equals 1, is not even, positive term. And then on the bottom, if you start with 1, you're going to start with a negative term. Okay, but they do the same trick. Now, here's what the alternating series test says. If you spot an alternating series, then as long as it meets a couple of requirements, all right, then you'll be able to tell if it converges. So here's what they look like. Negative 1 to the n times a sub n, or negative 1 to the n plus 1 times a sub n, or negative 1 to the n minus 1 times a sub n. So what you're doing is you're separating the alternator from the rule of sequence. Okay, here's the alternator, which just contributes the sign, and then here's the rule of sequence that contributes the magnitude. Okay, it's the main part. So it doesn't matter if it's n or n plus 1 or n minus 1. If then you look at the non-alternating part, just the rule of sequence, and if two things happen, if the limit as n goes to infinity of a sub n equals 0, which is kind of like what we do when we test for the nth term test, right? We check to see if the rule of sequence goes to 0. The alternating series test says if it does go to 0 and your terms are monotonic decreasing past a certain point. Okay? That means as you go up further and further, the terms get smaller and smaller and smaller and smaller. Then, if those two things happen, they get smaller and smaller and smaller beyond a certain value k. They could get kind of bigger in the beginning, but if after a certain point every term gets sequentially smaller, that's like the absolute value of it, and they go to 0, then here's what we can say. Then the series converges. Okay? Now, most of the time, the ones you're going to see, if 1 is true, number 2 is true, right? In other words, if the terms go to 0, you would think they have to be getting consecutively smaller, right? 1/2, 1/3, 1/4, 1/5. Those are going to 0, and they're also getting smaller. But every once in a while, you'll see one where the terms do go to 0, but they don't get monotonic decreasing sequentially. And I'll show you that. So here's what's cool about the alternating series test. It almost becomes the nth term test for convergence. Okay? Because most of the time, number 2 is going to be true when 1 is true. So usually when we just check to see if the sequence goes to 0, then we say that the series has an opportunity to converge. But here now we can say in the presence of an alternator, then the series will actually converge. And the reason that is because like if you look at 1 over n diverges, right? But if you have the alternator there, you're going to be subtracting every other term instead of adding all the terms. And what this says then is simply by subtracting every other term rather than adding together, you make the sum small enough, sufficiently small, that it does converge rather than get infinitely large. It's pretty neat, okay? So think of the alternating series test almost like the nth term test for convergence, but it has to be in the presence of an alternator. So let me show you what I mean. Example 16. You have that infinite series, right? Do you see an alternator in there? There it is. Negative 1 to the n plus 1, negative 1 to the n minus 1, or negative 1 to the n. There it is. So you focus on this. This is what we would call a sub n. That's it right there. What would be the limit as n goes to infinity of that? Is it 0? It's n to the first over n to the, so it's 1/2. So what's going to happen with this series? Is it going to converge or diverge? Diverges. Good. Why? 1/2 does not equal 0. So here's what's also true about the alternating series test. It's a one-way test. It's not a test for divergence. But when you do the nth term test for divergence, without the alternator, you take the limit as n goes to infinity of n over 2n minus 1. That equals 1/2, which is not 0. So this thing diverges by the nth term test, not the alternating series test. Because what's going to happen is you're going to get to a point down the line where you're going to be like plus 1/2, minus 1/2, plus 1/2, minus 1/2, plus 1/2, minus 1/2. And that's going to diverge. No, you wouldn't have to. No, you wouldn't have to. I'm just saying that I just wrote it there because it diverges, but not by the alternating series test. The alternating series test is only a test for convergence. So again, I like to sneak those in there on you. We learn a test, and then the first example of the test doesn't apply because we're using the nth term test. So let's look at B. Do you see an alternator there? I do see an alternator. So let's focus on the non-alternating part. That's what we're going to call a sub n. What would be the limit as n goes to infinity of that? 1 over the natural log of 2n. So which one goes faster, top or bottom? Top. So for large values of n, is that sequence going to approach 0? No, it approaches infinity. Oh, so this thing actually diverges yet again by the nth term test. Man, I'm sneaky. Okay? This one's going to alternate between negative infinity and positive infinity. So it diverges by the nth term test. So why would I introduce the alternating series test and give you two that are alternating series but diverge by some other method? Well, surprise you. Yeah, keep you on your toes. All right, how about this guy? Is this an alternating series? Why is it here? Cosine of pi n. When n is 1, we get cosine of pi, which is cosine of pi, negative 1. Negative 1. When n is 2, I get cosine of 2 pi. What's cosine of 2 pi? 1. When n is 3, I get cosine of 3 pi, which is negative 1. Is that contributing only a sign, or is it contributing also a magnitude? The top for positive integer values of pi, 1 pi, 2 pi, 3 pi, 4 pi, cosine is going to alternate 1, negative 1, 1, negative 1, 1, negative 1. Guess what? Meet another famous alternator in disguise. This is an alternator in disguise. And it's the most famous alternator in disguise, which means the cover's blown. It's no longer in disguise. You just throw it into the category of things that alternate. Now you got to be careful. It's sine of n pi, that doesn't work. Sine of n pi are going to be multiples of odd pi halves. I'm sorry, odd pi. That'd be 0, 0, 0, 0. That doesn't work. Okay? But if it were multiple of odd pi halves, then it would be 1, negative 1. But we typically don't use that one. So this is an alternator. So what we can do then, by the alternating series, is separate it. Here's the alternator part. And then this is what we would call a sub n. So we'll check the two things. What's the limit as n goes to infinity of 1 over n? 1 over n goes to 0, right? It goes to 0. That's the first thing. Do these terms then get monotonically smaller? 1 over 2, 1 over 3, 1 over 4, 1 over 5, they get smaller and smaller and smaller. So, because of the alternator there, this series converges by the alternating series test. Now, if you wanted to say it, you'd have to say since the limit as n goes to infinity of 1 over n equals 0, and 1 over n is monotonic, decreasing for n greater than or equal to 1, which is where we're starting. Then the series converges by the alternating series test. Okay? So this is kind of interesting. If the alternator were not there, if I just started you off with sigma from n equals 1 to infinity of just plain old 1 over n, what would we say about 1 over n? It diverges. Okay? So that would be your divergent harmonic series. But again, in the presence of an alternator, we subtract every other term, which makes an otherwise divergent series small enough to now converge. Pretty darn interesting. We're going to call this one in the next little section here on the notes. We're going to call this one conditionally convergent. Why do you think we would call it conditionally convergent? It converges under the certain conditions, and that condition is, of course, the presence of the alternator. With the alternator there, the series converges. We subtract every other term, makes it small. Without the alternator there, series diverges. So it only converges under the condition that the alternator is there. So you might be asked, is it conditionally convergent? Or the other thing we're going to talk about is absolutely convergent. This one is conditionally convergent. But you also might just be given this on a multiple choice, and this might be like one of the series that they give you, and I'll say which of the following are convergent. And I'll have like Roman numeral 1, 2, and 3, and combinations of. So this one is convergent. All right, how about this one? Do you see an alternator? Yes, the alternator is this whole thing. So we're left with 1 over n factorial. That's a sub n. Does that go to 0? Yes. And the terms do get monotonically smaller because every time you add something to n, it gets bigger, which makes 1 over that number smaller. So this one also then what? It converges. Now, let's kind of just talk about the idea of conditionally versus what's going to be known as absolutely convergent. If I took the absolute value of this rule of sequence, the absolute value of this sequence basically gets rid of the alternator. Because what does the alternator really do? It makes the terms positive then negative, positive and negative. If I take the absolute value of this sequence, now all the terms are positive, which is essentially getting rid of the alternator. So we know it converges in the presence of the alternator. The question is, if the alternator were not there, and we were adding all the terms instead of subtracting every other one, would it still converge, do you think? Do you think 1 over n factorial goes to 0 fast enough on its own to converge? It does. Yeah, because remember, exponential goes to 0 fast enough, and factorials grow faster than exponentials. So this one converges with or without the alternator. So this one is going to be called absolutely convergent. Which almost sounds like you're just doing emphasis. You sure it converges? Absolutely. I'm certain. But really, you could say it converges absolutely, meaning the absolute value of it. The positive version of it does as well. We're actually going to learn something called the ratio test that'll show or prove that 1 over n factorial converges, but not yet. All right, this one here, you see the alternator? There it is. What's left without it? You're left with 1 over that. Quickly, do you think that converges or diverges? It converges. Good. Because we have the alternator, you can get rid of it. And we're left with really 1 over n squared. 1 over n squared is going to go to 0. And if you go out far enough for larger and larger values of n, these terms will be monotonic decreasing. So this one converges by the alternating series test. The limit of 1 over n minus 5 squared plus 1 goes to 0, and the terms are monotonic decreasing. Do you think it converges conditionally or absolutely? In other words, if the alternator were not there, would 1 over something n squared converge on its own? Yeah, it would be compared to a p series, 1 over n squared, which would converge because p is greater than 2. So this is another absolutely convergent alternating series. All right, how about this guy? Converges or diverges? This one converges. We've already actually seen this one. This is another alternator. When you get rid of it, it's 1 over n, which is your harmonic series. Yeah. So in the presence of the alternator, the alternating series test says if 1 over n goes to 0, which it does, and the terms are monotonic decreasing, which they are, then the series with the alternator in place converges. Okay? That's a problem in and of itself. But then the follow-up question is, does it need the help of the alternator to converge, or can it do it on its own? Well, it needs the help of the alternator, because if you got rid of it, you're just left with 1 over n, which now will add every term, and that's your harmonic divergent series. So yeah, this is, again, what we're going to call the conditionally convergent harmonic series. It only converges in the presence of an alternator. All right, sweet. Here is the idea I've been alluding to, the idea of absolute versus conditional convergence. So here's the theorem. It says, if the series from 1 to infinity of the absolute value of a sub n converges, that means if all the terms are positive, and when you add them all up, that gives you a finite number, then without the absolute value, the series converges as well. So what does that mean? Well, there's two cases. If a sub n is already completely positive, all the terms are already positive, then what does taking the absolute value do to each term? Nothing. So it's going to converge, of course, with or without the absolute values because they're unneeded. The only time it really matters is if you have some negative terms, which would be like in an alternating series. So if it converges on its own without having negative terms, you add them all up and you get a finite sum, then getting rid of the absolute values is only going to possibly make the sum smaller, right? If you have any negative terms. It's only going to make the sum smaller if you have any negative terms because you're subtracting. And of course, by comparison, if something converges, then anything smaller than it will also converge. Okay? So that's what we were just doing. You check to see if something converges. Cool. And then you look to see if you got rid of an alternator or made all the terms positive, would it still converge? If it does, it's absolutely convergent. If it doesn't, if it needs the negative terms or the alternator, then we call it conditionally convergent. All right, so let's do this again. It's kind of the same idea. We have an alternating series, -1 to the n over the square root of n. Is this one conditionally convergent? Is it absolutely convergent? Or is it just straight up divergent? Sometimes having an alternator doesn't mean it converges at all. You could have like +1, -1, +1, -1. That one diverges by oscillation. What do you think? Diverges, converges absolutely, or converges conditionally? It's conditionally convergent. Very good. Because we have the alternator. Cool. Cover it up, and we're left with 1 over n to the 1/2. Now, 1 over n to the 1/2, does it go to 0 as n gets bigger? Yes. Do the terms get monotonically smaller? Yes. The square root of 5, the square root of 6, the square root of 7. Okay? It works. So, this, in the presence of the alternator, converges. So, it's at least conditionally convergent. Now, how do we test for absolute convergence? Get rid of the alternator and pretend you walked up to the problem and you just saw 1 over the square root of n, which is the same as 1 over n to the 1/2. Would 1 over n to the 1/2 on its own converge or diverge? It would diverge. It's your divergent p-series. The power is 1/2, and it's less than or equal to 1, so it diverges without the alternator. It needs the alternator to subtract every other term out to make it smaller. So this would be conditionally convergent. So it's kind of neat. You have these divergent series, but there's hope for them. If you simply subtract every other term, you can make an infinitely large sum small enough to be finite. Pretty nifty. All right, how about this one? We see the alternator, so let's do the alternating series test. Cover up the alternator. It's still part of the series, but you cover it up. You're left with 1 over 3 to the n, which is exponential. Does that go to 0, 1 over 3 to the n? Very rapidly, right? Do the terms get smaller monotonically? 1 over 3 squared, 1 over 3 to the cube? Yeah, they do. So this one converges by the alternating series test, which means it is at least conditionally convergent, yes? Now let's test for absolute convergence. Cover this up now and pretend it was never there. Now you're walking up to just 1 over 3 to the n, which is the same as 1/3 to the nth power, right? And what is 1/3 to the nth power? This is a geometric series. And the absolute value of r is the absolute value of 1/3, which is 1/3, which is less than 1. So it's really like an exponential decay. So does it converge on its own without the alternator? It does. So it doesn't need the alternator's help. The alternator is going to make the sum smaller, but it's already finite. So anything that's smaller than finite will just be still finite. So this one we say then is what? Absolutely convergent. Ooh, convergent. I wanted to come back up here. And I wrote it in pink, so I missed it on the previous example. Before we move on to the alternating series remainder, it's hard to imagine a series where the terms go to 0, but they don't get monotonically decreasing. And you're not going to see a whole lot of them at this level, but they're out there. For instance, if you look at 1 over n squared minus 1 over n, okay, what's happening to the terms as n goes to infinity? They are going to 0. 1 over n squared goes to 0, and 1 over n goes to 0. So the terms are going to 0. But is this one monotonically decreasing? Well, I don't know. Let's see. Let's go ahead and start expanding it out. By plugging a 1, I get 1 over 1 squared, which is 1, minus 1 over 1, which is 1. Okay, so there's the first. I plug in a 2, and I get plus 1 over 4, minus 1 over 2. Plug in a 3, you get plus 1 over 9, minus 1 over 3. Plug in a 4, you get plus 1 over 16, minus 1 over 4. Now, the 1 minus 1, those don't really count. They cancel each other out. So, plus dot, dot, dot. Yeah, these might cancel out. Maybe something down the line might cancel out. Maybe not. We'd have to go out a long way. But notice what's happening here. With the 1's gone, because you get 0, you have plus, minus, plus, minus, plus, minus. So there's no visible alternator in the expression, but do the terms in fact alternate? They do, okay? Do you think this one converges or diverges by the alternating series? Well, if you just looked at the first one, we see they alternate, and you just say that the terms go to 0, you would say it converges. But there's always that second one. Are these terms without the plus or minus, okay, the absolute value of the terms, are they monotonically decreasing? 1/4, 1/2. Did we go up or down? We went up. 1/2 is bigger than a 4th. 1/2, 1/9. Now we got smaller. 1/9, 1/3, we got bigger. 1/3, 1/16, we got smaller. 1/16, 1/4, we got bigger. What's going to happen as we go down the line? Small, big, small, big, small, big, small, big, small, big, small, big. Is that monotonic decreasing? No, it's not. So, this one is inconclusive by the alternating series test. So here's one where even though the terms go to 0 and it alternates, we can't say it converges because the terms don't monotonically decrease. What do you think? What is your intuition? You think this one still converges or diverges? Diverges. Good. Why? It does. Because the fraction keeping not small enough. Some of the terms are getting small enough, right? But some of the terms are not. If you think of this as two separate integrals, you have a convergent p-series minus a divergent harmonic series. What is finite minus infinite? Infinite. This is a divergent alternating series. Okay? I will see y'all hopefully at the pep rally and hopefully tomorrow morning at 7:30. We'll have fun on a Saturday morning.